Currently, Madam is a faculty member at Channabaseshwara Institute of Technology, Gubbi. She teaches mathematics and mathematics-based computer science courses at undergraduate and postgraduate levels. Madam, on behalf of the entire participants, I welcome you to this session, ma'am.
Yeah. Thank you. Thank you for the introduction. So here in this post-lunch session, we are assembled to do some maths. Yeah. So I'll just share the screen, and then we can start. Yeah. So we will be learning today, or whatever, refreshing today, cryptographic hash functions. Now, can you hear me? Am I audible?
Yes, ma'am, you are audible.
Okay, thanks. Thanks, Anil sir. Okay, now this cryptographic hash functions uh, is used a lot nowadays in blockchain and blockchain technology. Now, we keep hearing things like cryptocurrency. So the crypto in the cryptocurrency comes from cryptographic hash functions. They're so intrinsic to today's technology, because any security technology of today almost definitely will use cryptographic hash functions. So now let's just, since we are just coming from lunch, let's just get to start from the basics. So if you're talking about cryptographic hash functions, what is a function first? We all know that you have an input and called x, and you get an output fx, right? For our purpose, let this be the definition of function. Okay, next, what is a hash function? Now, hashing, the word hashing, the English word hashing means make a jumble or channa gotaiskudu. That's what hash means. Just mix things up. So a hash function would be what? It takes as input some string. So that string is generally called a key or a message digest, and it does something, some hashing, some mixing, cutting, and turning from one place to the other. That kind of operation it does, and it gives this output string, which we will denote by h of this x. X is the input string, the key or the message, and this is the output string, the digest. It is called, the output is often called the digest, hash value, just the hash, like that, checksum. These are some of the common names for the output of the hash function. Now, hashing has been used, most of us are from computer science backgrounds. We've seen hashing before. Hashing was used a lot for data storage and retrieval, so that it efficiently you can retrieve data, avoiding linear searches and things like that. Used in databases a lot. So that familiarity is there with hash functions, but more recently, in the more recent decades, hash functions of a certain kind called cryptographic hash functions have come to a lot of use. So what is the main thing about cryptographic hash functions is that, of course, as is obvious, it is used in security applications. And an important feature of it is it has some specific properties. Okay, now before we actually go to cryptographic hash functions, let us just see a simple hash function. What is this hash function? Let us say you have a book, you have a library. In that library, somebody borrows a book. Now, what is generally done is you write down whatever there'll be an accession number and all. That is one kind of indexing. But say you don't want to do that. If that is there, the person has taken is clear to everybody. You don't want that. But you also don't want to return to you. So say the librarian comes up with this scheme that anybody can take the book before I issue the book. Say I'm the librarian. Before I issue the book, I will do something. What I'll do, I'll take the book. Say this is the book. Ruskin Bond is an author's name. Panthers, Moon, and Other Stories. So what I'll do, I may write down as though like a code. I'll write RB Ruskin Bond PMAOS Panthers, Moon, and Other Stories. So RB PMAOS. I'll write it down, and then I'll issue the person the book. Now anybody else who sees this RB PMAOS will not know what the book is, right? Oh, so then I tell my colleague who, if somebody returns this book, so and so person, just check if this matches. So if the person brings this book back and the person and my colleague sees, this is the first initials of the author and then the first letters of the title of the book. So that's a way of verifying, the book that the person took is the same as the book returned. But in between, when the person was seeing just RBPM AOS, they could not make out really, so easily at least, they couldn't make out what is the book that they had, the person had taken. Say I suggested this scheme, but now my colleague said, see, no, it's easy to guess. RB means the initials of the author. How many authors will you have RB? This is easy to crack. Think of a better thing. So she suggests this thing, this hash function. What she says is, go to page 10. Okay, I open page 10. If this is page 10, go to the fifth word. First line, fifth word. What is it? It is climbing. So take the first letter, C. Then go to page 20. Say I open to page 20. First line, fifth word. It is the. Take T. Like that, she says open 10, 20, 30, 40, 50. For each of these pages, go to the first line, fifth word, take that letter. Then I write it down. C, T, A, maybe page 40 had a word draw, so D, and page 50 had the word to, so T again. So this is my hash function. Now anybody, and I issue the book. Now anybody seeing that hash C, T, D, A, T has no idea which book I have taken, right? He has no idea what. Unlike that RB and first letters of the title, this is far more difficult to guess what the book will be. There's no way of guessing what the book will be. Rather, it's really very tough. Only when the book, if I have the book, if the book is returned, I can verify, yes, I can go to the 10th page, first line, fifth word, does it start with a C? Okay, yes, first thing, check, right. Like that, go to this 20th page, do the same thing. If all 10th page, 20th page, 30th page, like that, till 50th page, all 5 pages, first line, fifth word starts with the letter which I have written. Yeah, right. I can verify that this book is indeed the book that was taken. So this is the way a hash function is done. Now, cryptographic hash functions used in security applications have specific properties. Any kind of hash may not work. First, let's say a trivial property is about the output length. What is it about the output length is that it should have a fixed value, fixed length. The output length should be fixed. So just now I gave you two schemes. One was that RBPM AOS, Panther Moon and Other Stories, Ruskin Bond. So that was of variable length. If I take another book, How to Fly a Aeroplane, it will be HT fly an or FAA. That will be smaller, and it may be of variable length, so that won't do. But the second scheme suggested by my colleague, 10th page, 20th page, 30th page, 40th page, 50th page, it has a fixed length, five alphabets. So that is a fixed length. So that is one condition for cryptographic hash functions, that it should be of a fixed length. Another thing is they are all in bit strings, that is binary strings of zeros and ones. We want the output. This is a trivial condition because anyway all data, any kind of alphabets or numbers are finally converted to 0-1 strings. It can easily be done. You can take the ASCII characters and do it. So output should be bit strings. That is easy to see. The next criterion is very important, that it should be deterministic. What does deterministic mean? It means every time you do it, you you have an input x, you pass it through the hash function, you must at each time get back the same hash. Like, okay, this book example, every time 10th page you go, it will give you the same page, but it may not if the edition is different. Same book, but slightly different edition may give you different things. So any input, every time it should give the same output. So that is an important feature. So for any given input, the algorithm should produce the same hash value every time. That is this deterministic part. So one has to be careful. Whatever the string is put, fixed string, if you have a fixed input, whatever you have, it should give the same output. Here, what is the input string for this example, which the book example which I'm giving? It will be all the sentences in the book, chapter wise, everything, the file, what the person has, the file. If I input that, every time it should give the same output. It should, but some different formats, if I put it, I will get different output. So this scheme is not so deterministic. Another way where it may not be deterministic is, I may say, I will toss a coin. If it comes head, I will write RBPMAOS. If it comes tail, I'll write it the other way around. That may give a good hash function, but then I don't know whether you tossed a coin or not. So this is not, it would not be deterministic then. Okay. Second important criteria is that it should be one way. What does it mean to be a one-way function? So you have in this example, which we just said about the book and 10th page, 20th page, just see that example. If we have a book in hand, I have a book in hand, I can compute the hash function very easily. All I have to do is open the 10th page, go to the first line of the 10th page and check the fifth word. Fifth word, first alphabet, and write it down. Then again, I go to page 20, I look where 20 is, go to the fifth page, go to the first line, fifth word, and fifth word's first letter, I'll write it down. So it's easy. In a 1 minute, I can write it down one way. So from the text to get, from the input to get the hash function should be very easy. Now the other way, that is, if you have the hash function, we had C, T, AAT, something like that, 5 letters if we had, to get it the other way is very tough in this example, right? That's how it should be. From the hash function to crack what the input was should be extremely tough. So the function should be one way. So x to hx should be easy, but hx to x, the reverse engineer given the hash, should be extremely tough. It should be practically impossible. Then your hash function is a good function. Now, another property is it should be collision resistant. It should have collision resistance. What does collision mean? The English word collision means somebody comes on this side, that side, and dash into each other. So that shouldn't happen. In the sense, what it would mean is, suppose you have an x, that is a input string x, another input string x dash, but they both have the same hash output, like input, two different inputs but same output. If that is there, it is not such a good hash function. So that we don't want it to be. So we should choose hash functions such that it's extremely tough to find two x's, such that h of the hash of x should be equal to hash of x dash when x and x dash are different. It shouldn't happen like that. So our algorithm should be collision resistant. So if you check with that book example, it to find, so how would you do it? If my, for this Ruskin Bond book, it was CTATG, right? CTATG something. I found it, I kept it. Now to find another book which has exactly the same means, how should it be? The first 10th page, first word should start with a C. That in the second book, X dash book. In 20th page, first line, fifth word should start with a T, and so on. For all 5 points, it should match. Then you can find another book which has the same hash function as the original, my original Ruskin Bond book. So that is rather tough. Now, to check collision resistance, what one sees is the output space. What is the size of the space? So just let's do a rough calculation of what is the size of the space. If I have 5 spaces, that is, first let 10th page in the Vandu, 20th page from there 1, and so on till the 50th page. So 5 alphabets I will have, a string of 5 alphabets. So how many different possibilities are there? First space I can fill with 26, assuming we ignore lowercase, uppercase. 26 different possibilities, A to Z, anything it could be. Second one, we can fill in 26 ways. So 26 for the first, and so into 26 for the second, and so into 26 for the third, and so on, 5 places. So 26 power 5. So just roughly calculate 26 into 26, even if you put it as 25, 25 into 25, 625. 625 into 625, it will come to some huge number, 4 lakhs something, 4.5 lakhs into 25. It will come to a huge number. So the space is very large. The output space is very large. So that's, if it is like that, our collision resistance, we hope, will be good. Of course, we'll come to, when, even though the space is large, there may be collisions, we'll come to later. But that space, output space, how big it is, that helps a lot. If you choose a output, lot of different output can be there, then we hope that there will be less collision. So that's the size of your output space is very important for collision. Now, I said if you have a large output space, you may have you think it is easy. So a lot of studies have been done on whether actually it's like that. This is in probability called the birthday problem. Anyone who has some little gone through probability problems, you'll see it's a very classic problem. What is the birthday problem? It studies how in a group of randomly chosen people, what is the chance that two people share a birthday, right? So you pick one person at random, you note the person's birthday, pick the second person at random, note the birthday, like that you keep on doing. How many people do you have to keep on picking till there's a collision, means two people have the same birthday? So roughly people say, you've read this, reading this, so you may get biased, but usually first thing what comes to the mind, 356 days, ignoring leap year. So 365 days, ignoring leap year, 365 days. So maybe by 2 I'll do. So approximately 180 people you have to pick. That is generally what people say. But actually, for in a group, by the time you pick, you do 23 people, if you have picked, there's a 50% chance that there will be a clash. That seems counterintuitive. You feel, yeah, nahi, it can't happen, doesn't seem like that. But you have a good rigorous probability proof for that it does happen like that. And that too in a group of 30 people, if you have chosen, there's a 70% chance that there will be a clash. So these birthday problems, series of problems, the probability used in them is what is applied for collisions in cryptographic hash functions. It's interesting. Most of us are teachers. We can give a lot of problems, hands-on problems to our students in a class of 50, check whether it's true, that kind of thing. So uh, it seems counterintuitive. You feel the space is 356, 365 days. It should take at least 180, but no, within 23 there's a collision. There is a 50% chance of collision, good chance of collision. So you can't, why I'm bringing this to your notices is not so straightforward to say that yeah, if you get a large space, there shouldn't be no collisions. No, they're very rigorous. Maths goes on for each algorithm to check how collision resistance there is, resistance the algorithm is. Now, there's another concept, target collision resistance. What is that? Like collision resistance, but a particular value. Like, say, there's a malicious hacker who wants to find something, you have x naught, he wants to find another x dash, say, such that x dash is equal to your original x dot. So in your birthday problem, it will be equivalent to, you want to see how many people you have to include, random people you have to include in the room, so that somebody clashes with your particular birthday. So that is, of course, even more tough, right? Target collision resistance, but that's what hackers are after, malicious hackers are after. Okay, so just these words we should know. And the fifth property is non-malleability or avalanching effect. So what does that mean? That means if in my input I make small changes, in my output it should not be also small changes. It should be very large changes. So a small change in x should result in a large change in the hash value. So there should be some metric for nearness, some way of measuring nearness. One way is Hamming distance. We know Hamming distances, two strings, bit strings, position to position. If they are same, that 0, 0, you say +1. If they're different, you say uh, you don't add it. A 1, 1, you add it. So you find the Hamming distance of the between first input and second input. If it's changed in a small way, you go and check the output before output, after output. If that's also changed a little bit, then it's not a good hash function. It should change a lot. Let us see if our book that book example, if you change the book, the whole or you say you have a small changes should not result in large changes. It should result in large changes. It should not be very close. So we'll do examples of that. So now let us, before we go to secure hash algorithms, the SHS series, which is now used for blockchains, a little more complicated this one algorithm. Let us see very simple examples and see if it where it satisfies these given criteria or not. Let's see an example of hash functions. So this hash function is a very simple hash function. What it does, it takes in the number, say 48 is the input, it adds the digits 4 plus 8, then divides by number of places which are there. So 2 places divides by 2, result is 6. Next one, say you have 1000. Any input can be any number. We'll say decimal numbers, the sort of numbers we are used to, and it will give an output. So what will be for 1000? 1 plus 0 plus 0 plus 0, that's 1. It divided by 4 places are there, so divide by 4. Result will be 0.25. You get the picture. 9999. So 9 plus 9 plus 9 plus 9 by 4, result is 9. So that's your hashing function, simple hash function. So let us check for whether it is deterministic. Let us check whether it's deterministic. What is deterministic? Every time you do it, do you get the same answer? Every time you add 4 plus 8 and divide by 2, you will get 6. So it is deterministic. Good. Check. It's a good, you can put a tick. It's deterministic. Is it one way? Let us try. 4 plus 8 by 2, we got 6. Knowing one way is what? If you know the hash, can you work back and find what the number was? So if you know it's 6, you don't know whether it has 2 places or 3 places or 4 places, very difficult. There are lots of values you can say. 8 plus 4 also will give the same thing. 657 will also give the same thing. So there can be lots of x's which give the result 6. So it is one way. You can't really, if you know the hash output, you can't really guess what the input is. Is it collision resistant? So I think since this is a talk where I just talk and you just listen, I'll only have to tell the answers. Is it collision resistant? No, because right now only I gave examples. 84 and 48 both give the same result. Any permutation of these digits give the same result, right? So it's not at all collision resistance, that way bad. Deterministic, yes. One way, yes. Collision resistance, no. Is it non-malleable? Let us check. What is non-malleability? Small change in x should result in big change in y. So now let us see this first example, 4 plus 8. Small change, 48, I make it 49. What will the average go to? 4 plus 9. So 4 plus 9 is 13. 13 by 2 will come to 6.5. That's close to 6. If I make it 1000, I make it 1001. That will be 1. So 1, 0 plus 0 plus 0, that is 2. It will come 2 by 4.5. So you can see that the 48 and 49 are close by, and 6 and 6.5 are also close by. 1000, 1001 are string wise close by. The result 0.25, 0.5 are somewhat close by. So this example is not malleable. It's not non-malleable, it's rather malleable. So it's not a very great hashing. Next, let's see a next example. Modulo 17. Take any number, take a modulo 17. So what is, okay, before that, this example, what was the output space? Least will be 0, right? Any number, if it's just 0, 0, 0, its average value will be 0. What is the any greatest value? Every digit, if it's 9, divide by that number of places, so you'll get back 9. So between 0 and 9, any digit you can get. So that's the that's your output space. What about for this next one? Next hashing candidate hash function is whatever the output, let's say m, the message m, let's take it as a numeric output. We do modulo 17 to it. So what are the modulo means? You divide by 17 and what is the remainder, that will be the output value. So any number, say 35, what will it be modulo 17? 34 will go, modulo will be 1, like that. Remainder, just recap if we have forgotten what is modulo. So what are the possible remainders? 0, 1, 2, 3, 4 till 16. So now let us check these values. Candidate 2, let us check deterministic. Yes, any number you put in, you put 100. If you divide by 17, remainder will always remain the same. So that's okay. It is deterministic. Is it one way? Yeah, yes. In the sense, if I know remainder is 1, it may be 18. 18 will give remainder 1. 35 will also give remainder 1. Like that, 170 plus 171, if you divide by 17 also, it will give remainder 1. So it is one way, but so seeing 1, you cannot really make out what the original message was, and which also shows it's not collision resistant. In fact, one way you can guess a bit, you can guess what the original message was. Like you can say, yeah, it is definitely not 40, because if the output is 1, modulo 40 modulo 17 is not 1. So you have, it is not really one way also. You can, it does give you some information. And it's definitely not collision resistant, because the output space is just 0 to 16, that's 17. So output space is small. Non-malleability is not, you change it little bit, you can, you make +5 change in the input, the output also will change +5, modulo 17, of course. So this is really not a good example. As we can see, it doesn't satisfy all the criteria. Okay. Another example is randomize and use. So you use a family, either take one or take the other, toss a coin. So that is not deterministic, but all these it will be. Right? We can come back to this later if we have time. 20 means there's much more to cover. Candidate 4. Let's just do this example. You take the message and multiply it by some constant, given constant, and another given constant. This is the hash value. You multiply the given message, the given input, you multiply it by a fixed a, then take modulo 1. Taking modulo 1 means what? Remainder after dividing by 1 will be the decimal part. You do that, multiply it by c, and then take the floor. It's a complicated function somewhat. So let us just quickly do one. Say a, you take it as, we have taken a as 0.43, the input as 47, then a into m gives you 63.21. If you do modulo 1, you get 0.21. Then if you multiply by c, you get 2.52. you do a floor function, you will get 2. So what happens? This gives output and a more randomized output between 0 and C, all values between 0 to floor. So 11, 0 to 11, all values will come, but it's not as bad as the previous modulo. In fact, it will follow, it will satisfy all these deterministic, one-way, collision resistance, no, because since you're doing floor functions, only 0, 1, 2, 3, 4 till 11, non-malleability it will satisfy. So it's much better than the previous example. So these are these 4 examples were to make you sort of alert about checking. You get a lot of candidate functions, hashes. All these criteria should be satisfied. So you need to be sort of comfortable checking all these criteria. If you are check for all, then you have a good hash function. So now, where are these? Let's just quickly do some places where they are applied to, some applications. So, easy application first, password storage and verification, somewhat similar to our book example. So if you have a password denoted by PW and you compute the hash function of that password and store it. So that is how authentication is done on systems. You have a password, the system is not storing your password. It is in fact storing a hash of your password. Every time it asks you, you type in the password, it computes the hash of your password and compares it with what is stored in its password database. It's comparing the hashes. It is not storing your password. So if you have your password is some secret, you keep it. It's not that the system administrator can open the files and see, oh, this is the secret. No, it's not like that. Only the hash is stored. So every time you type your password, your system computes the hash, compares the hash with what is stored. So your system can verify that it is you, but there's no way to retrieve the password, right? So this is where hash functions used in security. So similar in blockchains also, any data you store, you cannot get back what that data is, but you can verify whether the input is correct or not, assuming your hashing is satisfies all those 4-5 criteria. One thing here, a common doubt which arises is hashing and your ciphers. What is the difference? So the main big difference, because there are many differences, but the main conceptual difference is hashing is you get the hash and it is used for verification. It will immediately tell you if there's a change in the input, but it is not supposed to be, you just cannot reconstruct the input. Whereas in a cipher will be such that you give the input, it will make something, it will make it into cipher text, but that cipher text should contain all the information such that applying the correct decipher algorithm, you should be able to get back all the previous, whatever the previous input was, you should get that back. That is a cipher, whereas a hash is just for verification. You will not be able to, and you're not supposed to be able to get back the original input. Okay, next. This is the most important use, which is what is used in blockchain. All those transactions in blockchains, we heard, they are how to see that, a malicious attacker may modify some transaction. So that data should not be modified. As soon as modified, if there's a modification, it should uh, raise an alarm, raise a flag. So say there's a flag, there's a file F. There's a file F, and you store the file H of F, you store it. That file may be a file of transactions, it may be a receipt of anything, any kind of data file F. You compute the hash function and you store it. Anytime you get that file F, you want to see whether it was modified. So to check if it's modified, you recompute that hash F. If it matches with which was stored earlier, you say yes, it is okay. If it doesn't match with what you have stored earlier, you say no, there has been a modification here. So this is the important thing which is used in all these applications to check whether data is modified. This is the fundamental use of hash function. So in a blockchain, what happens in a blockchain? First, you will have the genesis block. That is just it will sort of the starting, some information will be there. Now the next block, what it will do, it will have, block 1 will have hash of the previous block. So block 1 will have genesis block 0000. Block 1's hash, as you can see in the figure, is 6u9p2. Say that's a hash, some hash, it is value. Now the second block that is chained to the first block, what is done? It will contain in its data, all those transactions are there in the second block. Another thing added to it is the hash of the previous blocks. As you can see, in block 2, the block 2 hash, how is it prepared? All the data which is there in block 2 regarding transactions, etc. Appended to that will be the hash of block 1. This whole input will be input to the hash function, and it will give the output of the hash of the second block. So hash of second block is by5c9. To get that, you use the hash of the previous block also. So, and like that for the third block, how you got data of the third block and hash of the second block is included. So both these two appended together is the input to hash function. Output will be hash of third block. Like that, you can see that third block has nested in it hash of second block, which has nested in it hash of first block. So if I make a change in block 1, that will show up in the hash of block 2, and in the hash of block 3, a flag will be alerted. So that's why you may, if you read do a blockchain thing, you will have heard that as you go, the block becomes older, then to change it becomes extremely hard. Firstly, changing the last block only will be hard, we will see with secure hash algorithm. But say you have a super computer and lot of resource, you will be able to crack it. If you crack it, you might be able to crack for the latest block. But to crack for block 1 means you have to work for block 2 and for block 3. The more deeply nested it is, the more work that will be required. You have to change the hashes of all of them. So now these are the standard algorithms used now for security algorithms, blockchaining, and so on. The MD5, message digest 5, SHA, secure hash algorithm 1 and 2, Now MD5 and SHA1 have been cracked in the sense, see, they are good algorithms. What has happened is you cannot guess. They are such good algorithms. Given the hash value, you cannot guess what the previous is, the input is. What can be done is complete enumeration. You brute force method. That's the only way to break these algorithms. But now with increasing amount of computation speed and efficiency of computation, they have even, it is even been able to generate all possible and crack it, all possible keys or the messages, and see where there is a hash. So if there is one collision, then it's said to be cracked. You can't do it anymore. So right now, what blockchaining and all these cryptocurrencies are mostly using is this SHA-2 family. 2 is itself a family. SHA-256 is the most used currently, but again that also is sort of, everyone has their fingers crossed. Currently it has not been cracked, but there is chance anytime that it may be cracked. So already newer versions with more even more difficult, it takes power to computing power to crack it. Those are Whirlpool, all these ones listed after SHA-2. SHA-2 is in bold because that's what is currently used. SHA-3 is there, which is in the development stage. But right now, SHA-256 is used. So what are the features? Let us just see. Main feature is SHA-2 has output of 256 bits. So now just let us, this is important. So let us just say 256 zeros, a string of 256 zeros and ones. So how many outputs, space, how many different outputs are possible? Let us see. Let us say there were only 2 bits, 2 positions. So what are the different possibilities? 0, 0, 0, 1, 1, 0, and 1, 1, 2 power 2. If there were 3-bit output, there will be 0, 0, 0, 0, 0, 1, like that. 8 outputs, 2 into 2 into 2, 8 different outputs. Like that, if there is 256 output, it is 2 into 2 into 2, 256 times. That's a very large number. So the output space is very large. Just to get an idea, 2 power 256 is approximately 10 power 77. That is 1 followed by 77 zeros. Even billion is 9 zeros, trillion is 12 zeros. So imagine 10 power 77 is a very, very huge number. So very large. And so no collisions found till date. So that's why it is used. What it uses a lot is logical operators, and, or, not, XOR. It uses this and other things also. It combines all of them. And just one thing here, just because your codomain of the function is very large doesn't mean there won't be collisions. That is a necessary condition, but it's not a sufficient condition. There can be bunching. The bunching means lot of things in that but small subset of the codomain, lot of uh, outputs may come to. For example, in our first example, we had, say, letters of the first first letter of the 5th word in the first line. So basically the first letter of a word. We said 26 different possibilities. So you feel, oh, it's a very large uh, space, codomain, 26 into 2. Even if you take only 2 words, 26 into 26, that is more than 625, very large. You feel like that. But what happens in English language, all are not equally likely. the alphabets, that is E, T, A, there is very much high probability of coming. Z, Q, very low probability of coming. So there is clumping. One type of subspace, lot of outputs go there only, so collisions occur. So these are avoided in SHA 256. If you draw a number line 0 to 1 followed by 77 zeros, all the outputs are uniformly distributed in SHA 256. That's a huge task. There are a lot of tests to see whether it is actually well distributed and things. So what is there? It can take input of any size. The SHA 256, it is broken up, cut into say to 512. Don't bother about the number. So if you have a large data, it's broken into those size, so that if it doesn't end with 512, it is padded. There's a method for padding, 1 followed by zeros, then the length of the message that is appended to the end. All that is available on the net. You can easily find it. These are all just numbers and constants which you adjust. So what is done is, first, to get it in multiples of 512, you do a padding of bits and append the number of length. What is the length of your original, you put that in the end. Then the initialize buffers are there. You initialize them with pseudo random numbers. How do you get pseudo random numbers? You take square roots of primes, first 8 primes, the decimal part of it, you put it like that. It's just made so that you really can't guess thing. Then the main thing is compression function. If your output is big, it is cut into n chunks. Then these chunks, chunk by chunk, and or not, shift operators, shuffle means permitting them, truncate means what is there you just cut off and leave what is there. All these operations happen in the compression part. Yeah, we're really running out of time. We should just go quickly over this. So this is a sort of diagram of what's happening in the machine. And this compression round, it does it 64 times in a loop. And final output is again XOR, so with something. So XOR, if you see, first string you see right here. Where's the mouse? Just a sec. Yeah. You XOR them 0, 0, you get 0, 0, 1, you'll get 1. So now I've compressed 2 chunks into 1, and it's impossible from here to accurately tell what it is. You can make a guess. If this is 0, you know, oh, this is, this should have, yeah. So XOR is one of them, 0, 1, 0, 1. If both are 0, 0, both are 0, 1, like that you have done. Knowing the XOR, you shouldn't be able to tell what the original things are. Similarly, and this, both if they are 1, you get 1, otherwise 0. We all know and, or, not, XOR, all these. XOR, all these, you cannot, it will get compressed. Means here the 8 and 8 will get compressed. 16 bits have got compressed to 8 bits, like that. It will compress it. It will use all these XOR, NOT. These are examples of binary functions. 2 inputs, 1 output. XOR, and, or. There are unary functions also, like shift function and NOT function. This shift, right shift 1, each bit is shifted 1 to the right. So this 1 came here, this 0 came here. The last one, which has no place, is put in the front again. Rotate shift by 1 place. That kind of operations. NOT operations means just 1, what is 1, you make it 0. That kind of things is there in the round, inside in the compression now. SHA output produces a 256-bit That is, 1 byte is 8 bits, so 32 byte hash value. And that hash value is usually represented as a hexadecimal. Hexadecimal, as we all know, 0 to 15 digits. So 0 to 9, that is 10 digits you have. Remaining are A, B, C, D, E, F. Those are there. So hexadecimal digits. So 8 bits, that is 2 power 4, 16. Each one will become 1 digit, so little easier to represent. So let's say you input "have a good day," then this is the small string input. If you give SHA 256 this input "have a good day," then this is the output EE. This is the 64 hexadecimal digits. Now say I gave the same input. Can you see the difference? Is it the same input or different input? So it's all the same except H I've made capital. This is the output. So you can see it's quite, it's not at all similar. You can see the non-malleability feature at work. Small change in input X has resulted in large change in output HX. The avalanche effect. Avalanche means things for that falling effect. One thing snowballs in a huge difference in the hashing value. Next, collision attack or birthday attack. These are the attacks. Find 2 different keys. Okay, these attacks are there, but before I, okay, 2 minutes left. I'd like to share one nice site with you. Just a fun site. So this is a SHA 256 generator. Whatever I type, so this is a did you get something from this session? Did you get something? Compute SHA 256, and that will give you a good output. This is what this string. Did you get something? This string gave this output. This is the output, computed digest. So this is fun to play with. This is the output of the string. So okay, getting back to, okay, wait, I think I did stop sharing. Anyway, that's okay. I have just 1 minute left. What I'd like to say is, okay, thanks. If you have any questions, you can ask. Let me just share my screen once. So any questions, please feel free to ask. Otherwise, we can stop now. There's many more examples and things, but I think we sort of time up now. I've posted my email address. Just share screen. This is share screen. Yeah. So this is my email address. Feel free to contact me if you have anything, any questions. This is my email address. So thank you for this sitting with me through this just an overview of hash functions. Next, Dr. Pradeep will go in with some more the cryptographic algorithm for the elliptic curve cryptography. So we'll continue now. Thank you.
Thank you, Shalai ma'am, for accepting our request and being part of this discussion.
Thank you, Anil sir. Thanks.
Okay. Okay, next we have Dr. Pradeep CR sir. So to know more about Pradeep sir, I'll request Professor Suhas, Department of Computer Science, to introduce him.
Thank you, sir. It's my privilege and honor to introduce our speaker, Dr. C.R. Pradeep, sir. Sir has completed his bachelor's from Indian Institute of Technology, Kharagpur, and master's from Indian Institute of Technology, Kharagpur, and his PhD from Indian Institute of Technology, Bombay. And coming to his achievements, sir stood first among graduating students at IIT Kharagpur, was awarded Institute Silver Medal by IIT Kharagpur for best academic performance in master program, and also was awarded CSR UGC JRF, awarded Research Award by National Board for Higher Mathematics, was awarded Best Outgoing Doctoral Student for H1 IIT Bombay. Sir has published several research papers in peer-reviewed international journals, and Sir has been a regular referee and reviewer for many research articles. And Sir have been involved in bringing about awareness in biodiversity conservation and popularization of mathematics, and extensively lectured to wide spectrum of audience varying from school children to university students. Sir also was resident faculty at Mathematics Training and Talent Search from program NBHM for a decade, and is a regular speaker and mentor of DST sponsored Inspire program to motivate youngsters to opt for a career in the research. Sir has been a part of NCERT textbook writing team, consulting to Karnataka and Kerala State DSCRT for their summer maths program. Sir is a member of Board of Studies and examination for several universities and colleges, and Sir is in much demand for faculty development programs for various institutions across the state. And Sir is currently working in our college CIT as a professor in the Department of Mathematics, and previously in year 2002-2007 he worked as assistant professor in Indian Institute of Science, Bangalore. Thank you, sir. It's a privilege you being with us. Over to you, sir.
Yeah, thank you, Suhas, for kind words, and I thank organizers for giving me an opportunity to say something about elliptic curve cryptography and blockchain. I hope I am audible and visible. I have shared my screen. I hope that is also, you can see that. Is that correct?
Yes, sir.
Anil?
Yes, sir.
Yeah, okay, thank you.
Yes.
Correct.
Yeah. So at the outset, I must apologize, or I must tell you that I'm not an expert in blockchain. I really don't know too much about it, but I just know that elliptic curves are indeed used in blockchain, particularly elliptic curve cryptography. So I'll try to tell a few things about both cryptography and elliptic curves. Coming from mathematics background, elliptic curves are an extremely beautiful object. They have fantastic symmetries, a lot of beautiful mathematics over, it's not just decades. For 100 years, they have been studied, and very beautiful structure. So amongst audience, there are young people who want to take up research area in mathematics, computer science, cryptography. Definitely this elliptic curve gives a lot of scope. There are really a lot of things to learn in this. Okay, so that's just commercial for my mathematics part. So let me get on to what we want to do here today. So whenever I'm talking, if it is too simple, just tell me so that I can change gears. So I presume that most of the audience know what cryptography is. Essentially, it is, it's a science of private communication between entities on a public channel. Typically, Alice, Bob, so I thought I'll make Anusha, Bharat want to communicate, and there is this Chandan who is a bad person and he wants to listen to everything A and B are talking. But A and B are very clever. They will talk in such a way that even if Chandan has access to everything that A and B are speaking, Chandan cannot understand what it is. how to do this is cryptography. So I'm not going to give a course on cryptography now. I'll quickly go through the basics and brush up as quickly as possible what cryptography is required. Then I'll try to explain what relevance of elliptic curve in building up a crypto system. That's what the main topic of today's talk is. So typically this is how it is. A and B want to speak to each other, and C has access to everything they are speaking. Yeah, this diagram has not really come out nicely. Means, I typed it out in one PC and now it comes on another laptop. Everything has got changed. So what I mean to say here is, if A and B are communicating and C has access to all the communication, but still C should not be able to understand what A and B are talking. That's what talking or exchanging what information. So there are different historically. What today we call private key cryptography is what was passed off as cryptography. Cryptography means, again, let me recall, it's just science or art of two people talking to each other, communicating with each other, two entities communicating with each other with full access of the information to third person, but that third person cannot understand what this communication is. That's what cryptography is. And historically, cryptography was always confused with what today we call as private key cryptography. Of course, if A and B want to communicate, they must implement a common scheme. Both of them must agree on some common language, some common notation, some common symbols so that they can communicate. This is called private key cryptography. Means this is the first part. I don't want to spend too much time on this. So typically, let's see. Let me try to explain this in a physical model. So here is one place. There is a A and there is a B. A and B want to speak to each other, and people like me are sitting in between, and we have access to everything they are communicating. So typically, let me give this example. So say, for example, A writes a letter and puts it in a box and locks the box. Box is locked, and the box goes through me. Means I am the carrier. I take box from A to B, and I give it to B. If A and B have used the same lock, one lock with two keys. A has a key and B has a key, same key, two copies of the same key, duplicate keys. Then B can open the lock, open the box, see the message. So message, before B opened, even the message was in my hand, I could not open it and read it. This is a very crude and very, rough example of cryptography. It's very funny in the sense A and B are communicating through me, but I can't understand what they are speaking because I can't open the lock. I can't open the box. This physical model is transferred to digital setup. And here the important part is locking, the key with which A locks and key with which B unlocks are the same keys. That's a very important point. The key which A uses to lock and key which B uses to unlock are the very same. It's two copies of the same lock, same key. Lock is only one, but two keys. Two keys means not physically two different keys, but they are duplicate. One is a copy of the other. So you can make copies. Many people can communicate this way. So the important point is locking and unlocking is by the same key. Same key means not physically the same key. Duplicate key, but copy of the key is the same. Means if I have access to one key, I get access to the second key. You must have seen it in many Hindi movies, right? The person will take an impression of the key on a soap or something and go back and then make another key of the same type. And that key can be used to open the locker or whatever, the box. So it's one key, and if you make a copy of it, I will say it's the same key. That means same key is used for both locking and unlocking. And here the important thing is, if A and B want to communicate, they have to meet each other beforehand so that they agree on a common lock and two keys which are the same keys. I'm just trying to emphasize that the keys are the same. Same means duplicate. One is a copy of the other. So they have to exchange keys, or of course they can trust a third party, and trusted third party has to tell, oh, A and B want to speak to each other, you please use this lock and these are the keys, you take this key, you take this key. That means A and B both have to trust a third party. The third party will actually be very powerful because he or she can sort of do a lot of unwanted things. Means he might give the key to C also, and C also will be able to open the lock, but A and B doesn't know that C is also able to open the lock. So trusted third party is not a, we don't trust each other, all trust only God, that's all. So like that, here nobody trusts anyone in cryptography. So we don't want to have trusted third party. So key exchange becomes a problem. Problem means A and B will have to meet each other and decide on a key. For a long time, people thought this is what is cryptography. And today, of course, I'm not going to talk on this. Of course, it's very powerful. There are lots of things happening. Even now, finally, cryptography is private key cryptography. But what we are interested today is what is known as public key cryptography. The crucial thing, difference between public key cryptography and private key cryptography is the point which I was trying to overemphasize in the first part. That for private key cryptography, the lock is one, and key which you use to lock and unlock are the same. Same means two copies of the same key. But it was realized in last 70, 80 years that locking and unlocking are two different phenomena. Means, yeah, it sounds a bit difficult to accept. Locking of a lock, I can lock with one key, but to open the same key will not help. So it's possible to do that. I will give you a physical model of this. Try to understand what I'm saying. I can lock a lock with a key, but with that key, I can't open the lock. Opening, I need a different key. If I can separate these two, locking and unlocking are separated, that is when public key cryptography is born. So I'll try to give you a physical model of this. So let us take the same model where A and B want to communicate through several audience, and the box goes through everybody, but box is locked. How it is locked is padlock. Padlock means the press lock. So remember, there used to be a lock, even now it's available, I'm sure. You press it, it gets locked. Padlock or press lock is what it is called. So what I will do is, say for example, I'm B, and what I will do is I will make a padlock, not one padlock. I'll make several copies of padlock, make it available to everybody in the world, because I'm very rich. So I can make my padlock available to everybody, and that padlock has the key which is only with me. I'm not going to share that key with anybody. It's my private key. Publicly, I have given my opened padlock. So now if somebody wants to communicate to me, all that person has to do is to use my lock, write a message, put it in a box, press lock the lock, and send it to me. Now, no one else can open it because no one else has the key to open that. I'm the only one who has the key to open that. So that's my private key. So anybody can send a message to me. Anybody can lock a message to me, but nobody can unlock. So these are locking and unlocking are physically taken apart. Means how I lock is not how I unlock. I hope I'm making sense. How I lock is just by pressing. Physically, I just press the lock. Whereas to open, I can't physically remove it. I need a key to open that. So this is private key, public key. So I'll try to explain this in greater detail. The thing here is I must be very rich to publish my lock so easily available to everybody. But that is digitally very easy, because digitally the advantage is anything can be duplicated very easily. I mean, when we were younger, 40 years ago, or whatever, 35 years ago, you want to send a letter to 3 people, had to make carbon copy or Xerox copy or stencil or something, you have to make 3 copies of the letter and send it to them. But now in one email, same letter, it goes to 3 of them. So what I'm trying to impress upon you is digitally making copies is very cheap, very easy. So if I can design a lock made out of numbers, and I can make many copies of it and send it to everybody, and I have a private key to open that lock. I have to explain what this means. That's what I will do in the next next part of my session. So if I can make this all into a digital model instead of this physical model of padlock with one key, uh, that's what is public key cryptography. So let me, all this I have already explained. And similarly, if B wants to send message to A, B has to buy A's padlock. Similarly, B also should make B's padlocks available freely everywhere. Then A also can communicate with B. Of course, it has problems. There are authentication problems, signature, lots of problems are there. It's not as, this model is not as straightforward as it looks, but this is the idea. So how to make it digital analog? I will spend some time on it, but not much. In fact, the drawbacks also I told you, basically it's authentication. Means how do I know? For example, I'm getting the message. I get a message saying that this message is from whatever Anusha, saying that this, because Anusha has my public key, public lock, the padlock. So she sends it. Then I open and I buy Anusha's lock in the market and then send the message to her. But it's not Anusha, but it is Bharat who has been sending me message under the guise of Anusha. How do I figure that out? Because I have no way of figuring it out in this scheme. But this is, as I said, this is just a model. How to make sure that authentication means how to make sure that if I get a message claiming that this message is from somebody, how do I confirm that it is actually from that person? So there are problems, but they are easily solved using mathematics. So I'll try to tell a few of them. So so this is what I wanted to say. Public key cryptography is basically a bit more resource consuming. It takes more computation to perform public key cryptography compared to private key cryptography. So public key cryptography even now mostly is used for key exchange, and then once the keys are exchanged, private key cryptography can continue. And key exchange can happen not for every message, but maybe every day or every hour or every year or every month or whatever, depending on how much money I have or what are my resources, I can do this. So key exchange is what public key cryptography is mainly used for. And all this I explained. One of them is Diffie-Hellman key exchange protocol. So I don't know, I don't have too much time to explain all these things because I want to quickly get to elliptic curves. Very roughly, I will try to tell you. Here, two people want to exchange a key. Key means it's some sequence of numbers or some information. It could be anything. So that they both of them agree on a particular scheme of communication. So let me illustrate this Diffie-Hellman key exchange problem with a very common example of color. So let me get this straight. A and B are two people who want to decide on a common color. Means, for example, let's take a scenario in which our conference organizers is giving us a party at whenever after 3 days. And then say me and Anil are there. We are good friends and we want to show our friendship by wearing same color t-shirt. Both of us want to wear same color t-shirt to the party. But now what happens, there are many others, Suhas is there, Sridhar is there, many participants are there. They all want to know what color t-shirt will Pradeep and Anil wear to the party. So they're all waiting to know this. So they are following every conversation between me and Anil. What color will they wear? Now I will show you a scheme in which everything me and Anil speak will be available to everybody, but you cannot figure out what color t-shirt me and Anil will wear. We will wear a common color. That also I'll assure that both of us will come to a common color. Means both of us will agree on one common color, but in front of you. In front of you means you will have access to all the information, but you can't make out what that common color is. This is essentially Diffie-Hellman key exchange problem. I don't want to do it in numbers because I'll do the similar thing in elliptic curves. So here I'll just give an illustration. Those of you who know it, you can take a 5-minute break. Those of you who don't know, follow this. It's quite interesting. So first, me and Anil, what we do is we agree on a common color. We say red, and we also agree on a number 1. So all of you know we are talking red and 1. I still haven't explained to you what is this 1 doing. You will soon get to know. What I will do is, say for example, A is Anil and B is Pradeep. So Anil decides on a private color, yellow. He won't tell anyone. He won't even tell his wife. He will just keep one color that's a secret, yellow. And B, that is Pradeep, will decide on a color, keep a secret color, blue. Of course, Anil doesn't know that I have chosen blue, and I don't know Anil has chosen yellow because we have not communicated this. This is a secret color we are keeping in our mind. But what have we told everybody? We have told everybody red and 1. Of course, it's confusing. What am I going to do? Me and Anil have a scheme. What do? Anil sends mixture of 1 liter of red color. He'll go to market and buy colors. He will buy 1 liter of red color and 1 liter of yellow color. What are these colors? Red color is the color which both me and Anil decided in front of you, and yellow is the color which he doesn't know. Nobody else in the world knows except Anil. So he will mix red color and yellow color of 1 liter each. 1 is the number which we have decided beforehand. And he will send me this mixture of red and yellow. Red and yellow color both are liquid form. It gets mixed up well. And he sends it to my house. He says, you please give it to Pradeep. So he'll give it to somebody, I don't know, whoever else is coming to party, he can give it to them. And what will I do? I will take 1 liter of red, that is same thing which me and Anil decided in front of everybody, and 1 liter of blue, which is my private color. Means no one else, even my wife doesn't know that I have chosen blue. I mix up red and blue and send it through the same public channel to be delivered to Anil. Now, the public channel guy, whoever is in between, he knows that he is carrying 2 liters of paint. One of the liters is red, but he doesn't know what is the other one in both the mixtures. In both the mixtures are going through him. He knows there are 2 liters of paint in this. One of them is red. What is the other one? He doesn't know. Now, what happens? Anil receives 1 liter of red and 1 liter of blue, which is what I have sent him. And I receive 1 liter of red and 1 liter of yellow. I don't know that the other color is yellow, and Anil doesn't know that the other color is blue, but it doesn't matter. What do I do? Both of us, not just me and Anil, both of us, what do? We add a secret color to the mixture which we have received. So that means Anil now, he had his secret color as yellow, right? See, Anil's secret color was yellow. He has received 1 liter red, 1 liter blue, and he will add 1 liter of yellow to it. What have I received? I have received 1 liter red, 1 liter yellow. Now I will add 1 liter of blue, which is my secret color. Nobody knows. Now we will mix these 3 liters together. He will also mix his 3 liters together. Both of us have the common color because this dabba has 1 liter of red, 1 liter of blue, and 1 liter of yellow. This dabba also has 1 liter of red, 1 liter of yellow, and 1 liter of blue. But addition here is commutative. First, if I add yellow or blue, it doesn't matter. Final color is going to remain the same. This is the commutativity of the operation. And the person in between, even though the persons in between had access to 1R plus 1B and 1R plus 1Y, they can never get with R, 1R, what else was added. They cannot guess it at all. It's impossible. Of course, they can guess it by going to market and buying all the possible colors and keep mixing at 1 liter at a time to red color and try to match both the colors. But it will cost them a lot of money and then time also. And then by then party is over, and anyway me and Anil will come to the party with the same t-shirt. Like both of us will dip our t-shirts in the respective final color what we have got, put it for drying, and then come to the party. So both of us have come to a common color, communicating in front of everybody but none of you have been able to understand what that common color is going to be. This is essentially Diffie-Hellman key exchange program, key exchange protocol. Here, both me and Anil have exchanged information in the form of colors, and we have decided on a common color. Now, the problem is to convert this to numbers. Basically, what me and Anil have to decide on some numbers and mix up numbers in some particular way, and both of us must come up with a common number. That is what we want to do. How to do it, I will try to explain using elliptic curves. We will see that. So this is the story which I told you. Man in the middle attack. I did not tell you that. See, the person in between has one red and one blue, and one red and one white. If he takes little bit of color, little bit of this color, and little bit of this color, and mix them, he will have 2 liters of red, 1 liter of blue, and 1 liter of white, which is a different shade from what me and Anil will get finally. Which means the person in the middle cannot get actually the color which me and Anil are going to decide. Note, Anil has not told me his secret color. I have not told him my secret color. But we will come to a common color. That is the main thing in this protocol. The challenge is, how do I make this physical model into an information theoretical digital version? How do I convert it into numbers? That's a problem. Basically, I want commutativity of operations. Means assume this is some number, this is some number, this is some number. This is a secret number, these are public numbers. Not public numbers. This is public number. This is my secret, a secret. I'm sorry. This is my secret and this is a secret. So adding here, I want to add numbers also. So addition is commutative. So I'm not telling addition will work, but like addition, can I do some other operation of numbers so that whichever order I do, answer must be the same. That's the heart of it. Not just that, there is one more thing. Somebody who knows 1R plus 1B, but they know the people who are in the who are attacking, means those people in the middle have access to 1R plus 1B, and they know that 1R is there, but still they cannot get 1B. In the sense, I have a color, 2 liters of color, in which I know there is 1 liter of red. I cannot separate R and B. I cannot take away, even though I know there is 1 liter of red in this, I can't take away 1 liter of red, because if I could do that, then there is 1 liter of blue left. But I mix it up in such a way, in this process, mixing up happens in such a way that you can't unmix. That's the property of liquid here. But I want to use this kind of thing for numbers. Digitally, how do I convert this? That is the challenge. So 2 things. One is commutativity and mixing up so that I know one part of the mixture, but I don't know what is the other part of the mixture. That kind of problems is what one wants. There are mathematical names for that. They are called trapdoor functions. I will just give a very quick review of this. This slide is a bad slide. I have to correct this. But anyway, I'll just tell you. Anyway, I can't ask questions, so I'll just tell you. If I give you this number 1517, for time being, assume that you are not seeing the other side. I'll give you a number 1517. Ask you to find the factors. It will take you at least, even if you do it with calculator, even if you, whichever way you do, it will take you at least 2 to 3 minutes to find out the factors, which are 37 and 41. I have purposely chosen large prime numbers, 37 and 41. So 1517, first you will try to do it with 3. Of course, as you see 1517, if I want to, the question is, I'm asking you find factors of 1517. Means what are all the numbers which divide this and tell me in that order. Right? 1517 as product of primes. So first you will try to do it with 2. Obviously it's even not an even number, so 2 will not divide. Next you will try it with 3, and then you will see, oh, 3 doesn't divide 1517. And then you will try it with 5. Oh, clearly 5 doesn't help me. Then I'll try it with 7. Then you will see that it will not help me. Then I'll see it with 11, etc., etc. I'll keep going till I reach 37. How many ever prime numbers are there? You can count. All that you have to try. It will take you at least 3 to 4. However quick you are, it will take you 3 to 4 minutes to find factors of 1517. But in contrast, the ulta problem, the reverse problem. If I give you 37 and 41, ask you to multiply, you can do it in a nick of time. Like you don't need much time. 37 into 41 is very easy. 1 into 37 is 37. 4 into 37, I'll do that. 7 4s are 28 to 8, carry 2. And 4 3s are 12 plus 2, 14. So I'll write 148 below and 37 on top and add them. I'll get the number 1517 in no time. It takes you less than 30 seconds. So what I'm trying to tell you is, given a number, to find prime factorization is effort. But if I give you factors to find the number, it's very easy, very simple. This is such a thing is called a trapdoor function. Means I can go this way, but I can go this way, but to go this way is more difficult. Going one way is easy. Coming the other way is not easy. So that is the main thing with this concept is needed for public key cryptography. So factorization versus multiplication, both look similar, but to factor an integer, it takes more effort. To multiply takes very little time. RSA, that's the most famous public key crypto system. Rivest, Shamir and Adelman, very beautiful romantic stories about this RSA adventure. Very beautifully written by that, what's that name? Simon Singh. The book is called The Code Book or Code Breakers or something like that. You can Google it out. By Simon Singh. Very beautifully written. You should, anybody interested in vaguely in cryptography, or even if you're not interested, you read it. It's very nice. Story of how RSA came up with, and in fact, R and S are engineers and A is a mathematician. So there's a lot of leg pulling between engineers and mathematicians in this story. Read it up, it's very nice. I won't spend time on that, but I'm sure many of you know Rsa algorithm. Essentially, it is based on the fact that factorization is difficult, but multiplication is easy. That's the crux of it. Another problem like this. So once this RSA people devised this algorithm, which uses the fact that factorization is difficult, whereas multiplication is easy, people are hunting for other trapdoor functions, other procedures, which one way is easy, other way is difficult. So one of them is called discrete logarithm problem. Today I will explain a little bit of that. I'll explain. Okay, I'll explain this, no problem. Not discrete log problem in its generality, but I'll describe elliptic curve discrete logarithm problem in today's talk. So what it is, I will have to understand. That is the heart of elliptic curve cryptography. Try to understand here. What we are trying to do is, when we want to do elliptic curve cryptography, it's a public key cryptography. That means people should be able to send message to me easily. Means anybody can send a message, but no one else can understand that message, even though they have access to message. That is the point. And to do this, in today's talk, we will use elliptic curves for that. Firstly, we have to tell you what is elliptic curve. What is elliptic curve? First, let us understand what is curve. This is something which we know from our high school days or college days or whenever. Degree 1 equation, which is always it's written as ax plus by plus c equal to 0. It's a straight line. I'm a maths teacher, so I'll have to tell you all the mathematics. I can't leave these out. These are important anyway. This is a straight line. Degree 1 means x power 1 and y power 1, and c term has x power 0, y power 0. So degree of the term is at most 1. Means 1 means not exactly 1, at most 1. Similarly, not similarly. So two straight lines. The important point which I want to emphasize is, you take any two straight lines, they will intersect in at most one point. They may not intersect at all, parallel. But you can never have two straight lines which will intersect at more than one point. You must have seen all this Platons alternative kind of thing, where number of solutions of degree 1 equation, two simultaneous equations, is at most 1. It can't have more than 1. It very easily done. High school, class 8, 9, we do these kind of things. That it has one solution. Or of course, if it's the same line written twice, then it will become infinitely many solutions. That's a different issue. I'm saying two different straight lines will have at most one point in common. This is an important point for me. And you take degree 2, this we study in our class 11-12, a conic section. A general term, it looks like this: ax square plus bxy plus cy square plus dx plus ey plus f. You see, term degree of each term is at most 2. This is a degree 2 term, x square. This is degree 2, x power 1, y power 1, so degree is 2. This is y power 2, y square is degree 2 term. This is x power 1, y power 0, so degree 1. This is also degree 1, this is degree 0, but together it is degree 2 equation. Degree 2 equation is a conic. We know conics can be pair of straight lines, or it can be circle. We know x square plus y square equal to r square is a circle. It may be an ellipse. We have standard equations for these: ellipse, parabola, or hyperbola. So any of your degree 2 equation has to be one of these. It's a conic section. You take a cone, you take a section of the cone. One of them, any section of the cone will be one of these: pair of straight lines, circle, ellipse, parabola, or hyperbola. The important point for this is all what we have studied in our class 11-12. The important point for me is, you take any straight line, it will intersect a conic in at most 2 points. Here I am telling a lie. It's not actually, no, this is not a lie. This is correct. Any straight line will intersect a conic in at most 2 points. That's correct. You take a circle, you draw a straight line, it will intersect either in 2 points when it is 2 distinct points, or it will intersect at 1 point when it's a tangent, or it will not intersect at all. So till now I have not told any lie. Most probably I won't tell any lie. Let me see. So straight line intersect a conic in at most 2 points. You take a parabola, hyperbola, ellipse, pair of straight lines, all of them will intersect in at most 2 points, 2 distinct lines. So please remember that. Degree 3 curves, these are what are known as elliptic curves. So initially we saw degree 1 curve is a straight line, degree 2 curve is a conic section. Both these we studied before our PUC, and now here is degree 3 curve, which we never studied. So this comes as a, it's a beautiful topic of study in mathematics. Degree 3 curves, they look, not any degree 3 curve, they must look like this: y square equal to x cube plus ax plus b. There are standard transformations. You say, okay, I have some other degree 3 curve and how to transform it to this form and things like that. They are typically, exercises for people who are studying elliptic curves. I won't go into so much of mathematics. So I want to look at these kind of curves: y square equal to x cube plus ax plus b. They are called elliptic curves. And being mathematician, I can't just say and get away with it. So I want these conditions: 4a cube plus 27b square is not 0, because we don't want to know, at least in cryptography, we don't want to have something known as singular curves. Unfortunately, I won't have time, energy to explain these details. But any of you interested, please feel free to contact me. I can explain these things. So I want this extra condition: 4a cube plus 27b square must not be 0. What is a and b? Here it is there. Y square equal to x cube plus ax plus b. This number should satisfy this condition. Why, I won't tell you. You just take it from me that is satisfied. So this is a non-singular elliptic curve. Means there is no singularity, which means whatever, at every point I can draw a tangent. That is simplest way of telling that something is non-singular. Let us see. This is too much in the air. Let's see a specific example. So here it is: y square equal to x cube minus x plus 1. Curve looks like this. Here I'm cheating a bit. I'm writing everything in real numbers, real lines, but there is a lot more beautiful things happening with complex numbers or finite fields level. Some finite field level I had to take you anyway through this in this lecture. I had to talk about it. I will do it. This is an example of an elliptic curve. This is of the form y square equal to x cube plus ax plus b, where a is -1 and b is 1. So this is one example of an elliptic curve. This is how it will look. I want you to observe the shape of the curve. And this is another curve. Or unfortunately, this equation has not come. I think this equation is y square equal to x cube minus 2x plus 0.5. As I said, I transferred from one laptop to another and a lot of things have gone away. Anyway, don't bother. This is another equation. this, what you see in this slide, this is a curve, another elliptic curve for some other a and b. That's all. And here is another one, y square equal to x cube plus 2x plus 1. It looks like this. Here is yet another one. This also I don't seem to have, I mean, this equation doesn't seem to have come, so I can't do anything. But anyway, for some a and b, you will get this is the elliptic curve. Now what I want you to observe is in any of these elliptic curves, it is symmetric about x-axis. You see how x-axis above it looks, below also it looks like that. That means, I mean, that is expected, because if you put y instead of y, if you put minus y, it is still a solution. Means what I am trying to tell you is, y is, if you have this general form, y square equal to x cube plus ax plus b. Let's go to the general form, doesn't matter. Y square equal to x cube plus ax plus b. Y is equal to x cube square root of x cube plus ax plus b. So you can have plus, I mean, positive or negative. So y can be positive or negative. Both not can be positive or negative. Both are possible. Positive, if plus y is a solution, minus y is also a solution. What this tells me is, okay, if you haven't understood what I am trying to tell, or I am not put forward properly, try to understand that this curve is symmetric about x-axis. This is important for me. About x, if I keep a mirror on x-axis, whatever is above looks the same as below. Essentially, because you can replace y by minus y. That's what it means. Okay, that is one thing I want to observe. And then any straight line intersects an elliptic curve at 3 points. I told you, any conic, any straight line would intersect it at 2 points. I told you a circle you take a straight line, it intersects at 2 points. If you take an elliptic curve, you take any curve, it intersects at 3 points. This is very important for my cryptography. Yeah, it sounds funny. What is this? All this got to do with cryptography and blockchain? But these are the building blocks for playing around with elliptic curve cryptography. These are the beautiful properties of elliptic curves. What I want to bring to your notice is point at infinity. Let me see how much time do I have. Another 15 minutes. So it's a bit difficult for me to explain this point at infinity. I will just my hand wave here and show you something. You see, let's take this curve. Most of the elliptic curves, not most, all elliptic curves will look like this. It will keep going up, 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 up like this, down, 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 down like this. In between, it will be a bulge like this, or it will be something like this. What you see in this. Here also something is going up, 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 up. Here something is going down, 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 down. Here also something is going up, 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 up. Something is going down. These are not straight lines, by the way. This is curve. This is very small view of the screen, so it looks like straight line, but it is not really straight line. This. So what I want to tell is, this curve you keep going to infinity. This curve will also go to infinity. Both of them will meet, and that point is called point at infinity. I know I am not telling you very clearly, because one has to use what is known as projective coordinates. It's not the real R2 coordinate like this. I'm showing you all on a piece of computer, piece of screen on a computer, which is a copy of R2, means R cross R, a plane. But there is something known as point at infinity. It goes all the way. So that point at infinity is also a point on my elliptic curve. Let's not bother too much about it. Only at one point I'll require. That time, if you want, I'll explain. Otherwise, don't bother. This elliptic curve any line meeting elliptic curve at 3 points is a consequence of a very famous theorem in mathematics called Bezus Theorem. It's a very beautiful theorem in algebraic geometry. So if you take any degree P curve and degree Q curve, they will intersect at PQ points. Not at most, PQ points with multiplicity and things like that. I won't go into details of this. But here right now, a straight line, degree 1, and an elliptic curve, degree 3, will intersect at 3 points. I want to explain this a bit more in greater detail. I will show you examples. There are very many beautiful properties of elliptic curves. There's no end to it. I don't have enough time to explain. Elliptic curves, one can give a 1 semester course on it. There are a lot of topology, geometry, symmetry, analysis, a lot of things are there. Very beautiful topic it is. So I won't go into all those details. The important thing is these elliptic curves have a group law on it. That means you give me, see for example on integers, if you give me two integers, I can add and get a third integer. I mean, that's what we have learned from our kindergarten, that you can add integers to get new integer, and then that addition follows certain basic properties which are listed here. Closure, associativity, identity, inverse, and commutative. Means closure means if I add two integers, the answer also will be an integer. Associativity means a plus b plus c. A plus b plus c is same as a plus b plus c. I won't explain all these things in greater detail. Identity means I have an element, for example, addition in integers, I have an element called 0, which when you add to any other element, I'll get back that same element. 5 plus 0 is 0 plus 5 is same as 5. 100 plus 0 also is 100, means I get back the same thing. N plus 0 is n. So 0 has that special property. That's called identity. Similarly, inverse I have, that means if you have 5, I have someone else called minus 5, such that 5 plus minus 5 is 0. So we understand these things. Commutativity is a plus b is same as b plus a. This is called an Abelian group law. Means if I have an operation on some set which satisfies these 5 properties, we say such a thing is called a group. The beauty is elliptic curve is a group. That is what is used very heavily. So let us try to see this. I didn't know whether I could do this, so I had prepared a set of slides here. Yes, Anil? Did you say something?
No, sir.
Okay. Group law, I will try to explain this group law on elliptic curves. So that means, what does it mean? If you give me 2 points on the elliptic curve, I should be able to tell you what is its sum, and that sum should satisfy these 5 properties. That means, if you give me 2 points on the elliptic curve, add them, the third point also must be on the elliptic curve. Associativity is a bit difficult to verify, I will not bother about it now. Identity I should show you, that means I should show you a point on the elliptic curve such that if you add any point to that point, I'll get back to whatever point I added. And inverse, that means if you show me a point, I should be able to show you some other point such that when I add these two, I'll get the identity. I have to tell you what that identity is. And commutativity, that means it doesn't matter whether I add A to B or B to A, either way it is same. So I'll just use this, give me 1 minute. I will use this graphing calculator and show you this elliptic curve group law. So this is y square equal to, I'm plotting this curve, that's all I'm doing, nothing much. X cube minus x plus 1. So this is the curve. As we said, this is the curve. Now I will pick 2 points on this curve. This is a GeoGebra. This is software called GeoGebra, which is very useful to show lots of things to our children, students. So I'm showing you one thing here. I will pick 2 points on this elliptic curve. I hope it's clear that this is an elliptic curve. Equation of this is given here. I have given here. Y square equal to x cube minus x plus 1 is what I have given. Now I will mark 2 points on this. This is point A and this is point B. Any point one can choose. I'll show you soon. Just a minute. I hope I'll be able to move this on. Yeah, okay. So now if 2 points are given on an elliptic curve, what I want to do is I want to tell you how to add these 2 points. What I will do is I will take a straight line. Where is the straight line? Here it is. So attached with a straight line. Here is the straight line. You draw a straight line joining A and B. I told you one of the properties of, so try to understand what I'm doing. Given 2 points on the elliptic curve, I draw a straight line, and I told you one of the properties of elliptic curves is that you take any straight line on any straight line will intercept elliptic curve at 3 points. Now I have already given 2 points. I have constructed the straight line using 2 points. So that means this straight line must intersect elliptic curve at a third point. Let us find out what that third point is. So I can intersect this line with this elliptic curve and I get this point E. Correct? So if you want, you don't believe me, you can, I can show it to you here. This is a move. You see here, as I move this A at different places, you see always there is a third point of intersection. Of course, it goes out of the screen here, but if you go sufficiently far, you can see that it will intersect. And similar, you can move A to anywhere. What is being shown to you as B is actually A. Means that's the first point I chose. You can move this also. What I'm trying to tell you is any straight line is intersecting this curve at 3 points, and if I start with 2 points and join them, I get a third point. Now what you do is you have to reflect this point in x-axis. I hope that reflection is there in this. I can't see that here. I'm sorry, this particular one doesn't have this laptop doesn't have the GeoGebra version which I wanted. I just downloaded it just before the lecture. Anyway, I'll just tell you orally. You take the reflection of E in x-axis. That means I'll get a point here. It should be there here. I'm not able to see that. I wanted to show you a reflection of this point E in the x-axis. That will come here. Maybe I have it on my slide, so you can see that. I'll show you here. See, I'll illustrate group law on x cube minus x plus 1. So this is what I do. Pick 2 points A and B on the curve. I'll define A plus B as follows. First, join AB. That means draw a straight line passing through A and B. Now find the point of intersection C with the curve. Means any straight line will intersect elliptic curve at a third point. So I have 3 points. So third point, I'm calling it C. And reflect C in x-axis to get D. That I will call it as A plus B. I'll show you an example here. In this example, I've chosen 2 points. I hope you can see it, A and B. And then I draw a straight line passing through A and B. Here is a straight line passing through A and B. And then I find the intersection of this straight line with the elliptic curve. This is C. And then reflect C in x-axis. I get a point here, this reflection. I will call A plus B as D. This is my rule for addition. I know many of you, if you have not gone through mathematics, you might find it funny or you might find it very convoluted. Why would anybody want to do this? You want to do it, if you want to do any transactions on Bitcoin, you need to do this. Means if you want to understand how Bitcoin works, you will need to understand this. Bitcoin, Ethereum, any of them use elliptic curve. I'll tell you which elliptic curve it will use also. So you take 2 points, join those two, get a straight line, it will intersect at the third point, reflect the third point in x-axis. That's why I said my elliptic curve is symmetric with respect to x-axis. Whatever is the third point, I'll call that as sum of A and B. And then one can verify that this satisfies all those 5 laws which I told you about being grouped. So this forms a group law on elliptic curves. Here is another example. This is another example, x cube minus 4x plus 0.5. So I'll choose 2 points. I hope you can see 2 points. One is A, one is B. And then I'll draw a line passing through A and B. This will definitely intersect the elliptic curve at a third point. I'll call that third point as C. And then I'll reflect this third point in x-axis. I'll get this point D. This is what I will call A plus B is D. This is the definition. A and B can be anywhere. You can move around A and B wherever you want. You will still, I mean, A can be on this component of the curve, this curve, and B on this, then also it will work. It will, all those 5 properties will be satisfied. I don't have time, energy to prove this. One important thing which we require for elliptic curve cryptography is what is A plus A. If I want to add A to A, how do I do? A and B, 2 different line points, I join. But if there is only one point A and A, I want to add it to itself, I draw a tangent at A. I can always draw a tangent. It's like B is coming from somewhere here. B is coming from here and approaching A. So then the chord AB will become tangent at A, and that will intersect my elliptic curve at a third point. Always it will intersect, because with multiplicity, any straight line has to intersect at 3 points. Here A equal to A, this is a multiple point, double point, and this is a single point, so totally 3. And then you reflect this here in x-axis, you get this point. This is 2A. This is the computation which is required for elliptic curve cryptography. How much time do I have? For 10 minutes. That's 10 minutes. I should be able to at least complete something. So I hope I told you how to compute 2A. 3A, if I want to compute, I'll add 2. This is 2A now. D is 2A. So I'll add 2A. This is 2A and this is A. So I'll add these two. That means I'll draw another straight line joining this point and this point. That will intersect my elliptic curve at a third point, and I'll take reflection of that. That will be the 3A. 4A, I'll add 3A to A. So I'll continue to do this. I can do this. That is what elliptic curve theory guarantees. And here are the group law, and then even the expressions are there. If you give me x1, y1, x1, y1 and x2, y2 are 2 points. Coordinates of x3, y3, I worked it out here on your screen. But it's not very important for cryptography. What is important for me is actually all the picture you saw till now, that's useless for cryptography. What you need to do is elliptic curves over finite fields. So I won't have time to tell you more about fields. Mathematically, I won't have time. But instead, I'll just give you a very quick crash course, 1 minute crash course on field. Field is somewhere addition and multiplication both make sense, and inverse of multiplication, division also makes sense except for 0. So such a thing is called a field. For example, we are all familiar with 0, 1, 2. This is a field modulo 3. Modulo 3 means you, for example, 2 plus 1 is 3. 3 divided by 3, whatever is the remainder, 0. So 1 plus 2 is 0. 2 plus 2 is 4. When you divide by 3, remainder is 1. So 2 plus 2, I'll call it 1. So you must have done this kind of computation. You can also multiply. 2 into 2, 4. Divide by 3, remainder is 1. So 2 into 2 is also 1. So I can do both addition and multiplication modulo 3. Answer will always be between 0, 1, 2. And they satisfy all those 5 laws which I told you for both addition and multiplication. So there is a standard racket which defines what a field is. So I'm not going to bother about it. Similarly, 0, 1, 2, 3, 4 is a field modulo 5. That means 3 plus 4 is 7. 7 means 7 modulo 5 is 2. That means if I divide 7 by 5, what is the remainder? That is 2. So 3 plus 4 is 2. 3 into 4 is 12. 12 if I divide by 5, remainder is 2. So 3 into 4 is also 2. 4 into 2 is 8. 8 means modulo 5. 8 divided by 5, remainder is 3. So I'll say 2 into 4 is 3. Like this, you continue. You can add, multiply any of these 0, 1, 2, 3, 4 with each other, and you will get another number between 0, 1, 2, 3, 4 only. Nothing else you will get. And that this addition and multiplication has very beautiful properties. 0, 1, 2, 3 is also a field, but not modulo 4. Unfortunately, this doesn't work. Means, for example, 2 into 2 is 0. That's a bad thing, because you are multiplying. In this last case, 2 into 2 is 4, which is 0, because 4 modulo 4 means if you divide 4 by 4, what are the remainder? 0. That's a bad thing. 2 into 2, 0 means I'm multiplying two non-zero numbers and I'm getting 0. That's not a good property. So modulo 4, it is not field, but there is another field structure one can put. I'm not going to go into details of this. In general, if you have a set with p power n elements where p is a prime and n is a natural number, then I can make it into a field. This is a very deep result in algebra. Galois theory tells you this. These are in fact called Galois fields, all fields of order prime power n. And all finite fields are like this. For example, you cannot have a field with 6 elements because it's not prime power. You cannot have field with 10 elements. Such things are not possible. So what we do is solutions of these equations, in these fields, they are called finite field solutions. And elliptic curves are solutions of these kind of equations in that finite field. To count the number of solutions is a difficult problem. I won't bother about it. There are specific algorithms, Schoo's algorithm, which can be used to count the number of solutions. I'm going to go very fast because I have just 2 minutes. So this is not going to be, I can't do this. So over F61, 61 is a prime number. I have plotted this curve y square equal to x cube minus x. That means it doesn't look like a curve because there are specific points. You put x equal to 8, then you see what is y. 8 cube minus 8 over 61. That means you divide by 61 and find the remainder. This is from Wikipedia. This is the curve. So people do elliptic curves, cryptography over such curves. And similarly, I've given you an example of other curves here. Elliptic curves get divided. There is very beautiful structure. What I want to tell is just 1 minute I'll take. If you take an elliptic curve over a finite field, that's what I explained to you what it means. You pick up any point G, any point, and keep adding G to itself. I told you how to add. You will get a point P. That is my public key. G, P and G. Knowing both P and G, you cannot compute K. This is a trapdoor function. You know P and G, but you can't find K. That means I know the point. I know I have, and then I will add the point to itself 10 times and I'll get another point. If I tell you the new point and the old point, you cannot find out that I have added 10 times. First point I added 10 times to get the second point. You can't find that out. That is essentially elliptic curve discrete logarithm problem, and there is no known efficient solution for this. So this can be used as for elliptic curve cryptography. Means if I choose an elliptic, A and B choose an elliptic curve or a prime field and a generator point G. This is like me and Anil choosing red and 1. This everybody knows. Now Anil will choose a random number A and computes AG and makes it public. And that means he is giving everybody, this is AG is what his number is. B, that is me, I will choose a secretly number B, compute BG and make it public. P, when I want to talk to Anil, I will take AG, which is public, and multiply it by my private key, which is B. So I'll get ABG. And if Anil wants to talk to me, he will take my public key, which is BG, multiply by his private key A, he will get BAG, but these are commutative, both are same. So both of us have come to the same conclusion. Both of us have the same number. Even though you know AG and G, you can't compute A. Even though you know BG and B, you can't compute B. So this is what is public key cryptography of elliptic curves. I've had some more things to say about how to add faster, but perhaps I will not do that because I'm running short of time. I'm sorry. Any questions, feel free to ask. And again, I thank all of you for listening to this talk patiently, and I hope I managed to convey some mathematics in the process. Any questions?
We can see your difficulties in making us to understand, sir, in 1 hour.
Yeah, this is a non-trivial topic because it takes at least 3 hours to tell all the details. But anyway, I hope I gave you some flavor of the subject.
Yes, sir. Participants, if you have any doubts, please ask now.
Of course, you can use my email address and ask me later also. No problem. Here is my email address. Thank you. I thank the
Okay, sir. Thank you, sir.
organizers for the opportunity. Thank you.
Okay, sir. Thank you, sir.
Yeah.